So today we are going over the Perceptron, a probabilistic model for information storage and organization in the brain. Saket there has the paper that I've been referring to. He has been going over it slowly and steadily, and he also did some homework on it, as I hear, which is very nice. This is supposed to be like a 75-minute, like very comprehensive talk. And the reason for this is that this paper is not like very theory heavy by any means, but it's very, I mean, it's not the end goal of what it wanted to do. Because following this paper, there was an AI freeze, there was an artificial intelligence neural network work freeze, where essentially, work stopped for a while when some of this was, almost refuted. There were two such freeze periods, and then the rebirth and revival of AI research started in 1994, where research picked up again, and then, where we are right now. But the point that this paper is trying to make is that what I'm trying to make with this paper is that this paper was essentially a foundation of neural networks. This is, where it was first proposed and started, and we owe whatever we have today for a great, number two, what this paper has done, which is Frank Rosenblatt's genius. So the Perceptron, a probabilistic model for information storage and organization in the brain, is what this paper is called. Um, we are at the ACM Academic Reading Circle meeting number 4. So congratulations to everyone who made it here. We have been doing this for a month now. First month. So that has been good. Uh, so essentially, I have tried to divide this seminar today, trying something new today. I've divided it into 4 chapters, and this is kind of the format that we'll have for our ARC sessions moving forward, which is where we pick up like 4 major themes from the paper and, compartmentalize it a little more so that we have like a better understanding of just these 4 chapters that we are trying to look at in the paper. Some more homework on my part is what I'm saying. Um, so the first chapter that we are looking, like without further ado, let's just get into the paper. As I said before, it's a 75-minute comprehensive reading session where I'll just go over these 4 chapters. You can, stop me at any point, ask me questions, but there'll also be reflections at the end of every chapter, 2 or 3 questions, which helps us like consolidate what we have been doing for a while now. Anyways, the first chapter that we are looking at for this paper is the mid-century computing landscape, which is essentially the intellectual, political, and scientific context during the age of 1958, because we need to understand where and what landscape this, event was happening in. Uh, I want to, before beginning, I do want to thank everyone for being here. We have been doing this for 3 weeks in the past, and this is our fourth one, and it's very, good to see that where we are coming here. The paper that we are dealing with here is, one of the most pivotal papers in artificial intelligence and cognitive science, Frank Rosenblatt's 1958 publication introducing the perceptron. Before we dive into the mathematics and the architecture, also the philosophical implications of this paper, we do need to understand why this paper mattered so profoundly when it was written and why it remains relevant today as you sit here working on robotics, autonomous systems, or modern deep learning contexts. Let me set the scene. It's 1958. The world is very different from today, obviously. The post-war intellectual ferment is happening. We are 13 years past the end of World War II, and the atomic age has just begun. Radar, computers, and communications technology have fundamentally altered how scientists think about information, control, and systems. This is the era of cybernetics, a term coined by Norbert Wiener in 1948. And cybernetics, for those unfamiliar, was essentially the study of feedback, control, and communication in machines and living organisms. Um, so feedback, control, and communication in machines and living organisms, which was a field called cybernetics, term coined in 1948 by Norbert Wiener. Here's the key intellectual insight. Scientists in the 1950s were beginning to ask a radical question. If you could engineer complex machines, which would be, guidance systems for missiles, automatic control systems, communication networks. Could you also engineer the brain, maybe? Could you reverse engineer cognition itself? This is a theme that we were exploring in the last paper that we read as well. But moving forward, Wiener's cybernetics proposed that feedback loops and self-correction systems were the fundamental unit of intelligence. So Wiener was saying that cybernetics is proposing, that feedback loops and self-correcting systems, as in backprop and fixing itself. Backprop is a term that will come later. Were the fundamental units of intelligence, and this wasn't purely theoretical. It was being applied at that time. The Macy conferences on circular causal systems and biological and social systems. I'll say that again. The Macy conferences on circular causal systems and biological and social systems, running from 1946 to 1953, brought together mathematicians, engineers, neurophysiologists, and philosophers. Norbert Wiener, John von Neumann, who the Neumann architecture for computers is built on, named after, Warren McCulloch, Claude Shannon, and others were literally asking the same question: why and what is the computational structure of the mind? This is the soil from which the perceptron that we are looking at grew. The Cold Wars and systems engineering. Essentially, there's another layer to this context, the Cold War. The Soviet Union launched Sputnik in October 1957, and this was just months before Rosenblatt had published his paper. In the United States, there was palpable anxiety about technological superiority because everyone was just worried that the Soviets will take over the space race and they'll just win. The American response was to massively fund research in advanced technologies, including early artificial intelligence. Rosenblatt, who was working at the Cornell Aeronautical Laboratory, which this paper was published at, if you go through the fine text, and this lab also had strong military connections, had access to computing resources and institutional support that was frankly extraordinary for that time. The perceptron machine itself, a physical device with photocells, potentiometers, and stepping motors, was built in this context of technological ambition and military investment. The Cold War wasn't incidental to the perceptron's development. It was the context that made it possible. The context being the space race just beginning and end of the World War, atomic age starting. Through this time, also what happened, and we have gone over this, is the Dartmouth Summer Research Project in 1956 and the birth of artificial intelligence, as we like to call it. In the summer of 1956, like we have discussed before, just 2 years before Rosenblatt's paper, something seismic happened at Dartmouth College. John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon organized the Dartmouth Summer Research Project on Artificial Intelligence. This is retrospectively the birthplace of AI as a field. The early attendees included Alan Newell and Herbert Simon, working on the logic theorist and general problem solver. He's also a very big designer, if anyone knows. He was simultaneously involved in 4 to 5 different fields and has given groundwork and fundamental work in all 5 of them, notably also working towards human computer interaction design and obviously artificial intelligence. Also involved was Arthur Samuel, who was working on the checkers playing programs. So these programs would essentially play checkers against another human player, and others. The intellectual mood was optimistic, sometimes even euphoric. There was a genuine belief that machines could be made to behave intelligently and that cognitive processes were fundamentally computational. So they were believing that cognitive processes were fundamentally a computation. There's two types of thinking that go that I have heard of. Even ASU has both think tanks. Well, one of them has moved completely to Rochester now, but that guy was Dr. Okay, I'm forgetting his name. Paulo Shakarian. He worked at the he Dr. Paulo Shakarian. He had the neurosymbolic lab at ASU. So there's like two types of reasoning that go with computation of the mind. Essentially, one believes in the neuron architecture, where they believe that everything is a programmed neuron, and everything has a weight associated with it and a bias that goes alongside. And this neural network essentially stores information in the forms of weights and biases. And Everything that you think about is essentially going through this weight and different weights combined together can, like, form your understanding of a concept or a memory, or, this is what I'm supposed to do. If you get burnt in your hand, you don't have to place your hand on top of a candle anymore because it does burn you. So that thing will be imprinted in your brain as, like, in the form of a weight and bias. And there's another, like, school of thought, which is neurosymbolic reasoning, which essentially says that everything is, like, Boolean logic. Like, everything is determined by XOR gates, NOR gates, OR gates, AND gates, and everything is like computable in that sense. So there's, like, these two lines of thinking that have been like, that have been around for a very long time. Anyways, moving forward. Uh, the Dartmouth workshop had the Dartmouth workshop had a particular philosophical flavor. It said that it was deeply committed to symbolic AI, like I was just mentioning. The idea was that intelligence emerges from symbol manipulation, from logical inference, rule-based systems, and discrete representations of knowledge. But Rosenblatt represented a different current of thought. He wasn't interested in any kind of symbol manipulation. He was interested in statistical learning, in connectionist models, and in networks of simple processing elements that learn through experience. He was working in a tradition that traced back to McCullough and Pitt's 1943 paper on logic and computation in neural networks, but he was taking it in a more biologically grounded and learning centered direction. Um, so we have a fascinating intellectual competition in 1958, which is symbolic AI led by McCarthy, Minsky, and Neitz, versus the connectionist AI, which were Rosenblatt and others, the Scruffies, as they'd later be called. Both were federally funded, though, and both were ambitious. Both claimed that they could, essentially solve intelligence. If I think of it, like, very intuitively myself too, I think that, like, logical reasoning is good until, like, a point, but how can you, like, make rules about, like, how can you generalize it to, that point? But I guess there's also simplicity in that fact. I do believe that, like, it's a more complicated, I mean, there's simplicity to that too when you break it down to the finer units, but I think the more complicated neural network architecture is what I believe. And maybe there's, like, a hybrid that we'll come to later on, that probably will explain things much better. But if you were to ask me, I would also believe in the Scruffies architecture. This rivalry, and it was a real rivalry, shaped everything that followed. Rosenblatt's scientific goal was to understand the information storage in the brain. That's what the name of the paper also suggests. Let me be very clear about what Rosenblatt was actually trying to do here. He wasn't just building an engineer's toy. He had a genuine neuroscientific ambition. He wanted to understand how the brain stores and processes information. At the time, there were competing theories about memory and learning. Uh, some people thought that memory was stored in specific neural pathways, which was a localist theory, and others thought that it was distributed across many synapses. Rosenblatt was drawn to the distributed storage hypothesis, and he wanted to build a model that could explain how learning could work if formation was stored probabilistically across many interconnections. The title of his paper is crucial: The Perceptron, a probabilistic model for information storage and organization in the brain. Notice, he says probabilistic, not deterministic, not rule based, but probability. This was a radical move for 1958. When work earlier had suggested that people were working towards deterministic architectures. Let's start with a question here before we move forward. Why do you think that Rosenblatt's focus was on probabilistic and distributed information storage would be controversial in an era dominated by symbolic or rule-based approaches to AI? Any thoughts on that?
Maybe you just wanted to think about it in a different way.
That's one way to look at it.
Yeah.
Yeah, try
Just
try something
easier.
new, easier. What do you think about, like, it being more explainable from, like, a natural, like, standpoint, like something that exists in nature, like work going on in the brain? Like, what do you think of that, right? Like, maybe he wanted to look at things from a, is this explainable from, like, a natural perspective or not? Because I know that when I put my hand on a flame where I shouldn't, and I see, like, a burn happening, and I feel the pain impulse, and, like, I want to take my hand away, it does treat me in a certain way, and a weight and bias are created in my, like, neural pathway that will never essentially let me do that again unless I want to get my hand burned, right? That is conditioning. Remember when we went over that example earlier, which was when a baby is born, there's like the first few, like, neural pathways that have to be genetically coded or coded in there. But later on, as life goes on, I mean, natural tendencies do take up and, form more pathways. But then the people that baby is surrounded by, the actions that happen around that baby essentially condition this baby's neural network and the mind, right? And then so maybe people were observing that, maybe he was observing that, and maybe he wanted to explore that, right? Like you were mentioning, explore it from a different perspective.
Yeah.
And like he said, maybe it was more simple because it was like naturally observable. This rule-based system was transparent, verifiable, and logically sound. Don't get me wrong on that, but
Yeah.
you can trace the inference here, right? But a probabilistic learning system is opaque. You can't necessarily explain why it made a particular decision. It learns from experience, like we were saying, and that experience shapes its behavior in ways that aren't reducible to explicit rules. For 1958, this was deeply uncomfortable for many AI researchers, and it still is in some ways. We still keep saying, right, like we were discussing earlier more, that like inference is one of the biggest problems that we are dealing with, and explainable AI would be like, it'll be groundbreaking. And a lot of people are trying to figure out, how to, and how at this point saying explainable AI is like, like saying the word Dyson's fair, honestly, because it does piss me off a lot. Where, someone will say the black box, I'm like, no, like, you, but it's gotten to a point where it's, that commonly like referenced now, like a black box AI system, because we literally cannot say what a neural network is doing inside, but maybe we can. Maybe we'll find out later in another ARC session plug. Okay. Okay. Um, let's think of another question here. Disciplinary tensions. So, yeah, I'll keep moving it. The other slide was supposed to be like a war slide, but
Yeah.
I was just going over it, so I didn't update it. Anyways, let's look at another angle here. What do you guys think of the computer scientists at Dartmouth? What do you think that the computer scientists at Dartmouth were skeptical about regarding Rosenblatt's approach? What do you think they were worrying about?
That would be inexplainable.
Okay, one way to look at it. Mo, you have any
I don't think they were worried because they came up with the probabilistic
Were they aware of the paper?
machine earlier than
They were aware of the Rosenblatt's paper?
They probably have to be, not a lot of AI researchers at that time.
Yeah.
Yeah, I mean, looking at a paper that was 2 years before,
Rosenblatt?
yeah, by Neumann, um, Shannon and McCarthy, and seems did probabilistic systems.
So they had explored probabilistic systems, right?
Yeah,
So why did they sit with deterministic then?
yeah, I don't know. First time looking at this.
Okay, another ARC session plug. Okay, we can explore it. The core tension was essentially that symbolic AI promises universality and compositionality. So it gives you universality and compositionality. You can build complex behaviors from simple rules like, binary logic. You can prove theorems about your systems because it's math. But statistical learning, especially back then with limited theory, seemed ad hoc, unprincipled, and limited to low-level pattern recognition. Rosenblatt's critics would argue that can you really build general intelligence from a learning machine? They had like, doubts. These doubts interestingly shaped AI's development for decades. Like I said, there was a AI winter. Um, audience, I would also like to add like, one more perspective before we move towards our second chapter, which is the historical perspective. The picture that I painted, right? These historical contexts that we have. Looking ahead to your own work, whether that's in robotics, ML engineering, or data mining, where do you see echoes of this 1958 tension between symbolic reasoning and statistical learning?
That's a question for you.
That's a question for you because you are taking data mining and excelling at it.
What was it? What was the connection to robotics?
As in, like, what do you see? Like, where do you see the echoes of this tension between symbolic and statistical learning, like in your work and like maybe robotics or ML engineering or data mining? Or is there none?
Yeah, there is always. And
There will be a connection.
robotics can't really have a lot of probabilism in example combat systems, and you can't just bomb the other town. So you've got to be careful on how
You need to be
much,
precise. Yeah.
not really, you got to be
Accurate, yeah, that's the word, yeah.
Fail.
No, 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 no. Don't even go there. Don't even go there.
Yes, you have.
Do you have any idea? This is 11th grade physics. Have you not been tortured with yeah. Okay. So yeah, you were saying.
So like, yeah, probabilistic systems are easier to build, but they come with a trade-off of not knowing what might be the output. And yeah, your risk is different in different situations. In bio, it's low because genes mean stuff. Example, if you're trying to like code for a new animal or like a extinct animal, bring it back to life, and can't depend on probabilistic systems. Because it might just I don't know, might not just be biologically grounded. So it's just depends because we're talking about memory, and memory is probabilistic in my opinion. So I think the risk here is much lower.
Hmm. Think of it like this, no? Even when you're like building an AI model, which is a probabilistic model, it has like a heat, like where where it predicts with a certain percentage that it's confident. The confidence percentage is going to say that yes, it's confident about like whatever output it's giving. The trade-off that you like get is an accuracy trade-off. You get a probabilistic measure, and then the trade-off that you get is an accuracy like trade-off. You measure accuracy. Um, anyways, I believe that I still believe though that like if you can't like with with like with determination you can't predict like A, then you do have to go with B, like a combat robotic system that's standing in front of me. If it has to have like a prediction in like in a percentage that like how likely am I the target that it wants to shoot, and if it can't shoot me, then which target does it actually shoot? Like it has to be a probability. I mean like that's the foundational framework that it's working on. Like okay, sure, like
Do like combat drones already exist? Like
they
autonomous
do, yeah,
ones?
they do. The issue like with today's like ML work is that we are applying more than understanding the fundamentals, and that is why like learning the literature is important. Another arc plug, but but another thing is that like and that's what like a lot of ML teachers are worried about, that everyone can build a model, but they don't even know what they are doing. They just know that this is how you train a model. You give it this, you give it that, and this is how it's trained. But what is the
Happening.
what is happening? Like,
Yeah.
and what really is this? Like, when you make like an image recognition model, how does it recognize the images? And can you exploit the fine tune, or can you exploit the fine lines that are in there, and then use it to your advantage to make an even better, more efficient model? People don't care about that. I mean, not all of them, but most people don't, and that's an actual problem. We looked at symbolic AI and connectionism. We went over the fact that symbolic AI deals with logic, rules, transparency, and symbol manipulation, and connectionism deals with learning networks, adaptation, and distributed representations. We see that McCarthy, Minsky, and Newell were symbolic AI advocates, and connectionism is something that, like Mo said, like they had also looked at, but Rosenblatt and others were the chief pioneers. Moving forward. Um, we move into like chapter 2 now, which is the Perceptron architecture.
Chapter 1 was just history.
Yeah, I was setting up the frame and setting up the landscape of when this was happening, a little bit of context, right? Because you do need to know why and what time frame this is happening, and I hope that was useful.
Yeah.
Anyways, chapter 2, also gives you something to talk about. Also, perceptron architecture. Let's do like, a deep technical dissection about what we have been setting up the frame for so far. So we essentially go from biological inspiration to mathematical rigor. We are now going to take a deep dive into the architecture of the perceptron. This is going to be mathematical and detailed, but I do want to emphasize something upfront. The mathematics is elegant and the ideas are very, very profound. Like I said earlier, this is not the end product, this is the foundation of how it started. Even though modern deep learning has superseded the perceptron in raw capability, most definitely, understanding the perceptron's mathematical structure is essential for understanding everything that comes after. There's three layers to a perceptron: the S units, the A units, and the R units. So I'm just gonna write these down for future reference by everyone. The sensory, the association, and the response. So S, A, and R. Um, the perceptron, oh, perceptron, um, architecture has essentially three: sensory, R, sensory.
I wish there was a light like on top of the board.
Light on top of the board. Yeah, we can do that next time. Um, this is association, right? Yeah. Association there. Okay. So if you look at the image that is present in the paper, of the perceptron, it should be on page number 3 or 4 or 5. Contains like three layers essentially. An S layer, which is called the sensory layer. These are the input units. In the physical perceptron machine, these were photocells. Photocells are cells that react to lights, photonics, 400 of them, arranged in a 20 by 20 grid. The S layer reads raw sensory data. Each S unit outputs a binary signal 0 or 1. The A layer or the association layer is where the Rosenblatt made a crucial design choice. The connections from the S layer to the A layer were randomly fixed. They were not learned. Rosenblatt initialized these weights randomly, typically plus or minus 1, and they stayed fixed throughout the training. This was inspired by the biological intuition that random connections in the brain provide a kind of substrate upon which learning can operate. Is this choice the right choice or not? Did it work or not? Let's build on that. The E units apply some threshold function to their inputs. Essentially, they fire if the sum of their inputs exceeds some value. So this value is called the threshold value. Like, you have mental capacity to be calm until, like, I poke you once. You'll be like, it's fine. I poke you twice. You're fine. There's probably like 300th time that I poke you that you will actually like say, please don't do that again. Right? That's your threshold. You cross that threshold.
Tolerance.
Tolerance. I mean, tolerance will be another word again.
Okay.
Tolerance will be something like, what do you do until the model breaks? So I'll say that this is the threshold. Threshold is like it waits until a certain like jar is filled and then it like fires a response. So that's threshold. Um, and the R layer, which is the response layer. This layer contains one or more output units. These are the ones that learn. The connections from the A layer to the R layer are initially random, but they are adjusted during training based on feedback, based on the weights and biases that change. Now I can see some of you might think here that why are the A layer weights fixed initially? That does seem inefficient, and why not just learn those as well, like the others. Well, it gets this is a good question, and it gets at the heart of why the perceptron did have limitations. Rosenblatt didn't have a way to efficiently learn the A layer weights. He didn't have the backpropagation algorithm. Backprop wasn't invented until the 1980s, and even then it took decades to become a standard, like I was mentioning earlier, right? Like self correctionism. So he used randomness as a kind of pre-processing step. One of our professors, Liu, says that uh, ran like when you don't have anything, then randomness is just better as a choice than having nothing. I mean, at least half of the times you can probably get your answer if it's a binary problem. He didn't have the backpropagation algorithm, like I said, so he used randomness as a kind of pre-processing step. The intuition was that random projections create a rich feature space. Then you learn a simple linear classifier on top. This idea is actually quite modern. Randomized features, random projections, kernel models, these are all related to Rosenblatt's insight that you don't need to learn every weight to get a good representation. The activation rule, which is the first mathematical thing that we'll get into. Let's get into the mathematics and geometry of this. We need to formalize the activation function. For an R unit, the input is the weighted sum of the A unit activations. Let me actually build the diagram itself. Can I have the paper, please? Yeah. So if you look at the architecture where I was talking about the S layer, A layer, and the R layer, it looks something like this. It's not really that difficult to honestly process. You'll have you'll have a you'll have an S layer with the photoperceptors that we were talking about. Photoreceptors that like we were talking about. This is the S layer. Which is the sensory receptor or projection area. And then we have the A units over here, which have a predetermined value, like the paper mentioned. There will be connections from our sensors to these different. This is the A layer, and then there's the R layer, where initially the connections are random, but as time goes on, let's take two for now. So R1 and then R2, and then there will be connections from here to here also. And it's not like definite or anything, but this is a good way to think about it initially. So there's the S layer, the A layer, and the R layer. Moving forward, we are talking about the activation rule right now, which is designated by this simple formula over here. It's not that complicated. It's pretty simple essentially, where we write y is equals to
Sine.
yeah. Let me just get into it. Give me a second. Not wearing my glasses. WIA it's theta. Here. Oh my God. 1 second. I can't see. It's tough getting old. Okay.
Okay.
Okay. In this formula, like you can see here, no. It's just screens. I can see
Okay.
all the things that matter. Okay. Okay. Here, AI is the activation of the ith A unit, which will be a binary value 0 or 1. Wi is the learned weight from the ith rule of the A unit to the R unit. So in this like step here, and then theta is the threshold, which is also learned. Threshold, like I was telling you, is like a finite like value until which an impulse can be fired. And the output y is a binary plus or minus 1, depending on whether the sum exceeds the threshold or not. In this formula, sine outputs a +1 if positive and -1 if negative. That's what sine is. Like quite literally, that's what sine is here. AI is the activation of input unit I. Wi, like I said, is the weight from input unit I to the neuron. Theta is the threshold, a constant the neuron must exceed to fire. And the summation I for every weight times activation is the weighted sum of all of the inputs. Sine, like I said, will output a +1 if positive and -1 if minus, and y is the final output of the neuron. Okay, perfect. Moving on from here. Here's like a beautiful part that you can think about in this equation. We can rewrite this a lot more compactly by absorbing the threshold into the weight factor. So you don't even have to think about the theta here. You can just absorb it into the weight factor, and they can essentially end up writing this equation right here as y is equals to sine W transpose A. Okay. Yeah. What does this mean geometrically? Well, in this aspect of in this space of A unit activations or feature space that we are dealing with here, the perceptron is finding a hyperplane that separates the positive examples from the negative examples. The hyperplane is defined by the W transpose A equals 0 that's written there, where all points where the WTA is greater than 0 are classified as +1, and the ones that are smaller than 0 are classified as -1. So everything in this, like, hyperspace, like just think of like hyperspace, like as a hyperspace as like a, like, a space where like all of the different like summations are like sitting. If like the W transpose A, like this multiplication gives you a value smaller than 0, then you essentially consider them as a negative, and then if they give you a value greater than 0, then you consider them as a positive, and then you just move on. That, like, it's it's just a classification that helps you get rid of the minus theta in this equation over here. The weight factor W is orthogonal to the hyperplane, which means that the multiplication is going to give you a 0. That's what orthogonality like means in linear algebra. The magnitude of W controls the sharpness of the decision boundary. The direction of W points towards the plus one side. This is a crucial finding because the perceptron is fundamentally a linear classifier. It can only solve problems where a straight line or hyperplane can separate the classes. This limitation will haunt us later, but for now, let's appreciate it. Linear, interpretable, and geometric. This is also one of the reasons why it was refuted and we did have the AI inventor. Uh, Newman and friends who got offended by whatever these people did. There were two more people. I can't remember their name at the top of my head, but they ended up refuting this by using one of their thinking, like symbolic reasonings, uh, which was his neural network framework failed when comparing with against XOR XOR. So that is what they used to refute his whole thing. But yeah, this is what will haunt us later. But for now, let's just appreciate it, where this system gives us a linear, interpretable, and geometric conditioning. The learning rule here is another piece of math, which is very simple. It's a simple equation that is very, very relevant even today on a very fundamental level with machine learning, um, which essentially starts with asking us a question about how does the perceptron actually learn. This is where most of the magic with machine learning that we think adjusting the weights and biases, this is where it actually happens. The perceptron learning rule is remarkably simple, which essentially says that the weight nu is equals to the weight old.
No, they can't see it.
You can't see this?
The camera can't see it.
Oh yeah, we can't really do anything about that anymore. But yeah, let's see. Okay. They might be able to now. Okay, it's essentially the weight old plus the factor, the learning rate times the error, which is t minus y, and the ith input activation. Let me write it here so that I can write more with it. The new weight will be equal to the old weight plus the learning rate times the error and ith activation factor. So very important. what does this equation actually mean? Let's go over it like very simply, because this is something that you will be needing or that you will be using all through your, I mean, through your machine learning journey if you choose to pursue it. Here, T is the target, which is the true label, +1 or -1. Y is the predicted output. So your true label, which is the label there, and your predicted output, the label that you predicted, or you want to predict, or you are going to predict.
Okay.
If you're benchmarking, then you want to predict. Okay. So there's going to be a true label, a predicted output. Both of them can have a value of +1 or -1. T minus Y is the error. If it's correct, then it's going to be 0. +2 or -2 if it is incorrect. Think about it intuitively, right? If your true label is 1, as in it's supposed to be 1, and then you get, as in you predict 1, right? 1 minus 1 is 0, right? If you have 1 as a prediction and your true label was -1, then it's going to be 2, right? So 2 or -2, depending on what was what. But whatever. T minus Y is the error. If it's 0, then it means that whatever you predicted was correct. And if it's -2, then it's -2 or +2, then it's incorrect. Nu here, N, is the learning rate, which is typically between 0.1 to 1.0. And AI is the ith input activation. So the numbers of input activation. The learning rule is an error correction rule. When the perceptron makes a mistake, it updates the weights in the direction that would have made the prediction correct. So that is right. When it's when it's right, there's no update. Let's think about this concretely. Suppose we present an example and the target is t equals +1, positive example. The perceptron predicts -1, which is incorrect. The error rate is t minus y, 1 minus 1, 1 minus -1, which is +2. For each input AI that was on at that time, so like think of a matrix and all of the A1, 2, A1, A2, A3, A4, A5. So for every A that was on, which was 1, we add new times 2 times 1 equals 2 new, which is the new corresponding weight. And what does this do? It increases the weights of the features that were on for this example, which were on for this example. This makes it more likely that the dot product, which was W transpose A, will be positive next time we see a similar example. The hyperplane has shifted slightly in the right direction. Do you see what happened here, right? Like this was like a form of like reinforcement where like if like something didn't feel right, which was calculated by t minus y, all of the net all of the neurons in that network that demonstrated the condition for that to happen, they were corrected. And all of the neurons that did not show that, which were the zeros in this case.
T minus y only limited like 2 and 0.
I mean, it depends on the type of architecture that you're trying to define. We are dealing with the perceptron's basic architecture here, so that's what we are dealing with. Yeah, and like the more complicated it gets, right, the more it's supposed to change, right? Like depending on the architecture of your reinforcement learning model, like it'll be a different framework, correct?
Change as in talking about the weights
Yeah,
being updated.
yeah. Or like how nuanced you're dealing with here. He's essentially asking if it's only going to be
Is it only correct or is it only wrong? Or is
like
it
he's asking if it's only +1 or minus. I mean, depend. It's like you count like in bases, right? Like so, think like I say that like every 2 units is 1 unit. So like when I say 1 2, that means I 1 2, and then I have to say 1 2 again, because 1 2 means 1 here. 1 2 then 2, 1 2 then 3. And then if you say you count 10, right? So like 1 2 3 4 5 6 7 8 9, and then 10. 1 2 3 4 5 6 7 8 9, and then 10. So you're thinking of that here, where like you're saying, oh, it can be a 1 or it can be a -1. That is why it gave you a +2 or yeah. I mean, that's a universal fact. So, it's more like you do a +1 or a -1, and then it adds up to a 0 or a +2 or -2. If you can have more states, which is like plus 1 plus 2 plus 3 plus infinity, minus 1 minus 2 minus infinity, then it will be anything. Like, you know what I mean? For simplicity, yes, we keep it here as that, but it can be anything depending on how complex your architecture is.
Okay.
So yeah, that's what I would say to that. If anyone's going to be watching this video and has like a better explanation, they can definitely like, you know, tell me. I'll convey it to Shubhadeep. Okay. Uh, what does this do, right? It increases the weight of the features that were on for this example. This makes it more likely that the dot product, well, W transpose A will be a positive next time we see a similar example, so that the same mistake isn't made again. So it moves its direction towards the correct, like, you know, value, or at least the perceived correct value. Similarly, if we misclassify a negative example as positive, we subtract from the weight, shifting the hyperplane to the other direction. This is beautiful in simplicity, but it's also limited in its power, and we'll see why later. We are coming to like another important question that we do need to ask, um, which is understanding, you know, the updating rule here. Why do you think that Rosenblatt chose an error correction rule rather than, say, trying to maximize some objective function like we do with modern gradient descent algorithms? I'll, you know, give like an answer for this. The answer is all that Rosenblatt like had was this at this time. He didn't have the mathematical machinery to define a smooth loss function and compute gradients. He had binary outputs, a discrete classification problem, and he needed a simple implementable update rule. The error correction rule is intuitive and practical. It also happens to be a special case of gradient descent on a particular loss function, the misclassification loss. We just don't know that. We just didn't know that yet. The perceptron convergence theorem, which is the mathematical guarantees. Here's what Rosenblatt's work, you know, becomes genuinely rigorous. He proved something remarkable, that the perceptron convergence theorem, essentially, which is that if there exists a weight vector that correctly classifies all training examples with a margin greater than 0, then the perceptron algorithm run on the training data will find a separating hyperplane in at most r square by that factor square updates, where r is the radius of that data. Keep that in your mind, and like, you know, uh, just think of it this way in plain language. The margin is the distance from the decision boundary to the nearest data point. If the data is linearly separable with a large margin, the perceptron will converge quickly. If the margin is tiny, it may take many updates. So it says that if there is, like, you know, a very large margin, the perceptron will be able to converge very quickly. But if the margin is tiny, as in the nuance of the correct solution is, like, you know, very tiny, as in, like, differentiating between a cat and a dog is much easier than differentiating between a husky and a chihuahua, like from what I understand, or like a golden retriever and a labrador, for a better example. Like, that's what this, you know, line in simple terms would essentially mean. um the theorem guarantees convergence to a separating hyperplane if one exists. Crucially, if the data is not linearly separable, the perceptron will never converge. It will cycle forever. Um this theorem was a landmark result. I can already see in my brain, like, you know, new ideas about how it's actually relevant even today, right? It provided a mathematical proof that a simple learning algorithm could indeed find a solution to a pattern classification problem. This was powerful evidence that Rosenblatt's approach was sound. But notice the condition. If there exists a weight vector that correctly classifies all training examples, this is a big if, and we'll come back to it later. It depends on the fact that, like, you know, it'll classify all training data examples correctly. There's also the linear separability assumption, which is the critical limitation uh, of his idea. What does it actually mean? The perceptron assumes that the input data is linearly separable in the feature space. It assumes that data is linearly separable. This is the moment where I want to highlight, you know, this critical assumption, and it underlies the entire perceptron framework. I'll say it again. The perceptron assumes that the input data is linearly separable in the feature space. What does this mean? It means that you can draw a hyperplane through the feature space such that all positive examples are on one side and all negative examples are on the other, with no examples on the hyperplane itself. Doesn't it sound flawed? To some extent. For many real world problems in 1958 and even today, this assumption is violated. The data is not linearly separable. There's noise, there's ambiguity, there's overlapping clusters. Real patterns in nature are often non-linear. And this is what our critiques used to destroy some of his assumptions too. Rosenblatt knew this. He wasn't naive. In his original paper, he discussed the use of random projections precisely because he could create new feature representations that might be more linearly separable. He was trying to sidestep the linearity problem by transforming the input space. By this workaround, he did realize that it had limits, and those limits would in a few years become the basis for a devastating critique. Now, let's think about the linearity assumption. Can you think of a simple classification problem that is not linearly separable? What would it look like geometrically? Can someone think of a problem that is not linearly separable, like, the dog and example that I was giving right now? No?
No.
Okay, I'll give an example. With that dog problem only, like it's easier to guess the difference. I mean, it's cool. Like you can say the difference between like a dog and cat or whatever. But
Yeah.
like even when you look at like two breeds of dogs, like they do have like similar structures. So if
Let's
two
use guitars then.
Okay.
Yeah.
Right? Like, yeah, like, oh my God, like which one of these is a Squire and which one of these is like a Fender, right?
Yeah.
Like how do you like actually tell the difference? Because a guitar is a guitar, like,
Yeah.
and there's more fine lines to it. And then, the factor, the ratio that I was saying, it'll be like much, much smaller. So it'll need like if like you can classify a guitar and a car in 5 training sets or steps, maybe classifying two guitars as two different species of guitars will take you like 50, 100 steps. You see the nuance and the simple logic that I'm going with here, right? Okay. Um, the Zor problem, which we'll discuss in detail soon, the concentric circles, the crescent moons, the interleaved spirals, these are all classic examples of non-linearly separable data. There's a historical note here that about the actual perceptron machine. Before we move on, let me give you a sense of what the physical perceptron machine actually was, because it's easy to get lost in the mathematics and forget that this was a real physical device. The perceptron was built at the Cornell Aeronautical Laboratory in the 1950s. It was built at the Cornell Aeronautical Laboratory in the late 1950s. It had 400 photocells in a 20 by 20 grid, which was the S layer, roughly 512 connected units, randomly connected A units, 8 output units, which were the R units, connected with adjustable weights, stepping motors that adjusted the weights during training, and a motor driven potentiometer that modified the weights based on error signal. The machine was about the size of a small refrigerator. Training involved literally running the machine, feeding it images via the photocell array, and letting the stepping motors adjust the weights in response to errors. Not a Python script. When it worked, it was genuinely impressive. The machine could learn to classify simple patterns like letters, shapes, etc. after exposure to training examples. But here's the thing, once you've trained it, you can't easily extract what it learned. You can't read the weights off and understand them intuitively. The weights are just numbers in a potentiometer. The decision boundary is invisible. The opacity, the inscrutability, became a serious philosophical concern. Yeah.
It's wild.
Um, let's think about machine learning's interpretability problem, right? Like the thing that they're talking about here, one refrigerator to rule them all. And this brings us to modern concept concern that is deeply resonant with your own, research. Um, how do you think the interpretability problem with the perceptron relates to modern deep learning? Are we facing similar challenges today? What would Rosenblatt think of a 100 billion parameter neural network?
It exists, right? Is a trillion parameter model.
What do you think he would think of this?
You'd be amazed.
Yeah.
He would think of
Maybe think of how to make it.
hmm,
Yeah. because you said he made like a physical like model of the perceptron. So
How many refrigerators would that be, right? This was like a 400, no, that was 400 perceptors. This machine can be called a 512 parameter neural network. Yeah, and we have a trillion parameter neural network now. Oh my God, that is a lot. Okay. That is like 20 billion times, like, more parameter. No, okay, I will not
what
say
do you
that.
do with
Yeah.
this many parameters?
It's just you get ChatGPT. The answer is well, we face even more severe interpretability challenges now because the net itself is so much more complicated. Don't even try to get lost in it because there's no point. But the question of whether we need interpretability is still hotly debated. In some domains like robotics, autonomous systems, and safety critical applications, interpretability is essential. In others, like image classification, we've accepted that some opacity in exchange for getting performance is acceptable. Rosenblatt would probably be both amazed and concerned. I don't know. I think he would be pretty fascinated by it. Chapter 3 now gets into limitations, triumphs, and the AI winter. Um, like I was just like a quick recap. Like I was going earlier on, the Perceptron was made at the Cornell Aeronautical Laboratory, and it had 400 photocells in a 2020 grid, which all had binary input 0 or 1 for simplicity. It had 512 units with randomly fixed weights, which was the A layer, and the output units were uh, with learned weights, just were adjusted when the training was happening, and this was the R layer. So S layer, A layer, and R layer.
Just using that formula.
Hmm?
Just using that formula.
Yeah.
Yeah.
There's two formulas that we went over. One of them was the computation where weighted sums are taken against the threshold. And there's another formula where we were talking about the hyperplane and simplifying it. We also talked about decision boundaries right now, like, being able to classify things as the negative or the positive, but it's not really that black and white. Again, see real world example, right? It's very philosophical too, like it's very philosophically applicable. We update the weights when predictions are wrong, and when they are right, we just leave them be. There's the learning rate n eta, which controls the step size, which is typically 0.121. And it's a very simple formula that we went over. The new weight is essentially the old weight, adjusted by adding the learning rate multiplied by the difference in the error, times the initial input. And then the error signal can be anything between a -2 and a 2. So -2, 0, and 2. Not anything, just these three. There's also the perceptron convergence theorem, which we briefly talked about. It says that if it's linearly separable with a margin greater than 0, then the perceptron algorithm converges at most r square by the limit square updates. And then, as I said before, if the separability is like large, like if there's a huge degree of separation, then it can be achieved in lesser number of steps because it's literally easier to separate these things. And if the separability is small, as in it's very nuanced, as in trying to find out the difference between Saha and Saket, then it's going to be a little more difficult. It's going to take more steps. Okay, great. Let's move on. Oh, and also there's a critical assumption, which is that all hyperplanes with a +1, like we can draw a hyperplane with all +1 on one side and all -1s on the other side. The requirement for this assumption is that we need linearly separable data. And in reality, many real world problems are not linearly separable. Rosenblatt knew this, but used random projections as a workaround, which gave him limited success. And also the fact that we were dealing with a physical perceptron machine. Um, Now we come into the third chapter, which are the limitations, triumphs, and the AI winter, where we went from euphoria to existential crisis in the artificial intelligence age. This also led to the first AI winter, where it just literally had to stop. Let's be honest that the perceptron was a triumph and a trap. The triumph was real. For a moment in the late 1950s and early 1960s, the perceptron looked like it might be foundation for machine intelligence. It was simple, elegant, and mathematically sound, and
Mhm.
it worked on real tasks. Rosenblatt was charismatic, he was ambitious, and he made bold predictions. He claimed that the perceptron would eventually be able to recognize patterns, identify concepts, solve problems, and exhibit human-like behavior. Spoiler alert, ChatGPT is doing all of that. 1958, Life magazine ran an article with a provocative headline: "The Navy device learns by doing," and quoted Rosenblatt saying that within a few years the perceptron would be, and I quote, "able to walk into a store, see a camera, and recognize it was a camera without having been specifically programmed."
That's a Navy device?
Uh, yeah, because
It was built from.
yeah, it was so. I think a lot of this core research was being funded by the not just the Navy, but uh, like during that time, like post-war, America was starting its heavy, uh, heavy, like basic scientific research drive, and that's why we are at where we are at today. A lot of universities were trying to focus on funding basic research because they believe that the way to get to more complex, more important, more groundbreaking breaking discoveries was to fund in basic research. If you didn't do that, then you wouldn't be able to, create real, and it paid off. Like, look, the amount of research that happened between the years of the 40s and the 1970s and even the 2000s, essentially, it's so many Nobel laureates came out, so much
Yeah.
work, so much hard science work happened. There was
Yeah.
the moonshot, which essentially meant that through 1969 they were trying to send people on the moon, and then Neil Armstrong did step on the moon. And it was groundbreaking, like this moonshot that the US invested in, simply because it was afraid that the Soviets might take over, but they did do it. It created so many different things across all domains, and all because basic science research was going on in the country. uh, so many inventions that we see today are a direct, I mean, an indirect uh, invention from a lot of other research that was going on. The mouse, the mattress, so many of these things were just NASA side effects, that came out, and we
Yeah.
simply wouldn't have them if this research wasn't being funded by the government. So we do owe, like, them that. Anyways, this assumption made by Rosenblatt was bold. It was, perhaps too bold, and it set off alarm bells among other AI researchers, particularly Marvin Minsky and Seymour Papert at MIT. These are the people who refuted and caused the first winter. Um, why was Rosenblatt? Why Rosenblatt was visionary and constrained? Uh, Before we dive into this chapter, we get to the critique, and but before we get to the critique, let me emphasize that Rosenblatt was genuinely a visionary. He did understand, and he really understood that learning is central to intelligence. He recognized that biological systems don't start with pre-programmed knowledge; they learn through interactions with their environment. He built a concrete working model of this principle that was revolutionary. What was it that constrained him? Well, there were several things. Limited computing power. The Perceptron was a special purpose machine. It couldn't train deep layers because of the limitations of early computers. Training even a three-layer network was computationally expensive. Lack of efficient learning algorithms. Backprop hadn't been invented yet, and the Perceptron learning rule works for single-layer networks. But how do you update the weights in intermediate layers? This was an unsolved problem. Theoretical blind spots. Rosenblatt understood that random projections might help create linearly separable representations, but he didn't have a complete theory of how many random features you'd need or how systematically they were supposed to be designed. The linear separability problem also comes in and creeps here, where it says that we come to the fundamental limitation that would dominate, like, this critique. And this critique is the Minsky and Papert critique, which was the ZOR bombshell, the XOR bombshell. In 1969, Marvin Minsky and Seymour Papert published Perceptrons, an introduction to computational geometry. This book is one of the most consequential critiques in the history of AI. It's where the term AI winter arguably begins. The core of this critique is elegant and devastating, and let me quickly walk you through it. Consider the XOR, the exclusive OR problem. It's a toy problem, but it's extremely instructive. The XOR is defined as follows. When the inputs are same, then the output is a 0. And when the inputs are different, the output is a 1. Let me quickly write it down so that it's more intuitive.
Okay.
Um, say we have the input as 0, 0, 1, 0, 0. So 0 and 0. When the inputs are the same, the output is supposed to be a 0, right? And then 0 and 0, 0 and 1, which are different. So you'll get a 1, 0 and
You're
1.
making like a OR table.
Oh yeah, I could have even done it with a 0 and 1. So I don't really need a bigger table because we are not dealing with 16 bits of logic here. We are only dealing with 4 bits of logic here. So I guess we can just break it down to this one. Yeah, so I guess we don't really need the other two columns because that would make it a little bit more complicated to visualize. I'll just get rid of those. That would also be a hexadecimal system. Okay, cool. So we have, when we have 0 and 0, we get a 0. When we have 1 and 1, we get a 0. When we have a 1 and 0, we get 1. And when we have a 1 and 1, we get 1. Oh, wait, when we have a 0 and 1, we get 1. So think of it this way, right? If it's the same, then you get a 0. And if it's different, then you get a 1.
Okay.
Very simple. This is the XOR problem. Now, can a single layer perceptron learn XOR? Let's think geometrically. We need to find a hyperplane that separates the positive examples, which are 0, 1 and 1, 0. 0, 1, 0, 1, and 1, 0, which give us 1 and 1. So the
Yeah.
positive examples from the negative examples, which are 0, 0 and 1, 1, which give you 0, right? So we need to find like hyperplane that separates the positive examples from the negative examples. Plot the 4 points on a 2D space. 0, 0 at the origin, 1, 0 at the right, 0, 1 above, and 1, 1 at the upper right, negative. Now try to draw a single straight line that has the positive points on one side and the negative points on the other. You can't do it. No matter what line you draw, you can't separate the positives from the negatives. The positive examples form a diagonal and the negative examples from the opposite diagonal. And the hyperplane you draw will leave some positive and negative examples on the same side. This is a non-linear separability of XOR. So let's try to point this on the number plot line here. Say I make 0, 0 here. I make wait, I make 1, 0 here, and I make 0, 1 here, and then 1, 1 here. Okay.
Yeah.
Here, try to draw a single straight line that has the positive points on one side and the negative points on the other. So which one of these are the positive points? So 0 and 1, which gives us 1, and then 1 and 0, which gives us 1. So these two are the positive points and these two are the negative points. Can you think of a single line that you can draw that will separate these and separate these? Can you? Can you also see that it makes like an actual X here?
Yeah, exactly.
Okay. Anyways, so these two lines are connected in a single line over here,
Yeah.
and it makes like one diagonal. And then these two are connected with this other diagonal.
Yeah.
Also, like no matter what you do, like you draw this, or maybe you try to say separate them over. There's no way to
You only use straight lines. Oh my God.
Yeah, so you can't separate them in a way that it keeps. Maybe we are looking at an answer later that I haven't clicked in my mind yet. So yeah, maybe it'll come with another paper that we will look at. Another plug. Now to draw a line in a straight line that has the positive points on one side and the negative points on the other, you can't do it because no matter what line you draw, you can't separate the positives from the negatives. The positive example form a diagonal, negative example from the opposite diagonal, and the hyperplane that you draw will leave some positive and negative examples on the same side. So this is a genuine problem, right? Like, and we just visualized it. Here's the Minsky and Papert's key insight. The perceptron can only learn linearly separable problems. Therefore, the perceptron cannot learn XOR. And here's where it seems like a minor problem at first glance, but XOR is a toy problem. But Minsky and Papert went further. They argued that many real-world problems are, at their core, non-linearly separable. Pattern recognition, concept formation, reasoning, these all require non-linear decision boundaries. That's why people say that it's not that black and white and other, philosophic. It's really not. It's not non-linearly separable. There's like too much happening, and you do have to make those curvy, bendy lines to actually come to conclusions about things or come to terms with things, right? Therefore, if a single layer perceptron, therefore, if single layer perceptrons can't model non-linear boundaries, they can't be the basis for general intelligence, which is a very fair thing to say. Audience, I would also like to go ahead and say here that when we think about non-linear decision boundaries as if they are real for if they are really important for real world problems or not, we should consider an example, which we should consider an example of different types of robots which are based on sensor data, where the classes that they are dealing with might be interleaved in high dimensional space. We can also think about recognizing objects in cluttered scenes or separating signal from noise in complex sensor streams. Many real patterns are inherently nonlinear, like the things that you're hearing right now. Like, how do you classify different voices from each other? You do have to like come to understand here that you are not like one linear layer of neural network that is sitting here. It's from what I think, it's like hundreds of thousands of very nuanced layers that have been trained through biology, evolutionary biology, where some things you will just hear and know are dangerous for you, and then you'll have a physical response to it. Like if it's supposed to be, if it's a
How do you explain instinct?
yeah, if exactly how you explain instinct, right? Those things are just evolutionarily fitted, in your mind, and you are trained for those weights. When our species stops feeling this threat for say 50 generations, then we will stop responding to that sound because we won't have heard that sound in such a long time, or maybe we won't, who knows. But this is what we need to look at. We are looking at high dimensional spaces here, spaces that have like hundreds, like maybe 200 layers, in their training, right? So it's not a linear, non-linearly separable problem. The obvious solution that wasn't obvious here is the fascinating part that Minsky and Papert underlined when they made the critique. They mentioned it in their book, actually. They used multiple layers. If you add a hidden layer between the input and the output, you can learn XOR, and here's why. Suppose you have two hidden units, H1 and H2. You can train them as follows. H1 learns to output 1 when the output is 0, 1 or 1, 0, i.e. it learns OR, right? You know how OR works?
Yeah.
OR is like when either one is 1, you get a 1.
Yeah.
And if neither is 1, then you get a 0. So it has the capacity to give you 1 75% of the times. Why? Because 1 1 will give a 1 0 will give a 0 1 will give you, and 0 0 will give you. Perfect. And this is layer H1. Okay, it's a hidden layer. So this H1 learns OR. Okay. And there's an H2 which learns to output 1 when the input is 0 0 or 1 1. So it learns NOR, which anything that OR does, you add an opposite to it. So it's NOR, right? This will give you a 25% chance of no, wait, this is a NOR, and it gives you a 1 when the input is 0 0, and
It's like the opposite for.
yeah. Yeah, it'll give you a 25% of percentage of getting a 1. Yeah, sorry about that, hindsight. The output unit can learn to output 1 when H1 is 1, and H2 when and 0 when H2 is equals to 0. So it learns and So if you look at this, then there's three layers now. There's the H1, the H2, and the output layer. And when H1 is equals to 1 and H2 is equals to 0, it gives out a 1. So when you compose these functions together, you have essentially solved XOR now. XOR, which is a combination of OR and NOR. It's also called exclusive OR.
Yeah.
So this can be like, signified with a very simple, like, not equation, but this can be visualized as such where XOR of x1 and x2 is essentially a function of ANDing an
Or and not.
OR of x1 and x2 and a NOR of x1 and x2. So why didn't this solution get implemented immediately after Minsky and Papper's critique? So we have to understand why the critique triggered the AI venture. And the answer to this is subtle and involves both technical and sociological factors. No efficient learning algorithm for deep networks were present. Even though multi-layered networks could theoretically solve nonlinear problems, no one knew how to train them. The Perceptron learning rule doesn't directly generalize to hidden layers. How do you update the weights of a hidden unit when you don't have the direct error signal? This is a credit assignment. This is the credit assignment problem. It stumped researchers for years. Computational infeasibility. In the 1970s and 1980s, computers were slow. Training even a small multi-layer network required massive computation. The problem seemed intractable. And there was also mathematical pessimism. Minsky and Papert in their book made pessimistic statements about the scalability of perceptrons. They argued that even with multiple layers, fundamental limitations would persist. They were wrong about some of these pessimistic claims, but the damage was already done. Um, Funding and institutional momentum. Also, when someone from MIT would actually critique something from the Cornell Aeronautical Laboratory as an instinct, thinking that MIT was literally established as the heart of all technological innovation, and it genuinely did have more government funding than the Cornell Aeronautical Laboratory, I would also get on a hate train and I would just support people from MIT. So the damage was indeed done. Funding and institutional momentum also created a problem where once funding agencies and researchers became convinced that perceptrons couldn't scale, like I was just saying, investments started drying up. The symbolic AI camp, McCarthy, Minsky, and others had been skeptical of connectionism from the start to begin with. Now they had ammunition to argue against it. Connectionist research became unfashionable. Sociological dynamics. There's a winner takes most dynamic in research funding. Once symbolic AI became the dominant paradigm, connectionism was marginalized. Researchers working on neural nets faced skepticism and had difficulty getting papers published and grants funded. So Zor, huh? The result of this was the first AI winter, lasting roughly from mid 1970s to the early 1980s. The connectionist research was largely abandoned, and neural networks went from being a hot topic to literally being black water. What research momentum was actually lost. So the tragic part is that the problems that seemed unsolvable in 1970s were solved in the 1980s. Backpropagation, which was an efficient algorithm for training multi-layer networks, was rediscovered independently by several people, including David Rumelhart, Geoffrey Hinton. I know you have heard that name. He's a Nobel Prize winning physicist. And Ronald Williams in 1986. He's also credited to be the father of modern AI because, he was taking it out of the AI winter. Um, it was actually invented earlier by others but hadn't been recognized as important. This breakthrough should have reopened the field. But the institutional inertia was real. By 1986, symbolic AI had dominated AI research for 15 years. Researchers had built elaborate expert systems, knowledge bases, and logical inference engines. The symbolic AI camp had deeply invested intellectually and institutionally in the idea that learning wasn't central to intelligence, that explicit knowledge representation was what mattered. So even after backprop was discovered, it took another decade before neural networks were taken seriously again. This period, roughly between 1973 and 1995, is sometimes called the second AI winter, though it was less severe than the first one. Let's think of the contingency of the AI history, which raises a profound question. What do you think would have happened if backprop had been discovered in 1970 instead of 1986? Would the history of AI have been different? Do you think deep learning would
Like faster. Maybe
Yeah.
like the concept would have been made earlier.
Yeah.
There wouldn't have been any hardware to back it up.
Yeah, I think it would be like quantum computing, right? Where like all
Yeah.
these algorithms do exist, but we really don't just have the
Exactly.
architecture right now to feasibly support it, right?
Yeah.
What do you think, Mo? You want to say something at this?
It's funding right now.
That is true. Uh, Man, I wish he had thought about Zor in his thing itself and written down ChatGPT can make mistakes like uh, himself, and that would have saved him some trouble. Uh, well, the answer is nuanced. Let's add like a sub question to this, that if knowing what we know about the deep learning success, do you think Minsky and Pappert's critique was fair, or did they underestimate the potential of multi-layer networks? What can we learn from the historical episode about the dangers of premature pessimism, right? Don't have all naysayers in your
It's like, why are you trying to coin innovation? Right?
yeah.
Why are you trying to keep it only within MIT? Right.
It's not that pessimistic,
Yeah.
but like it's not that pessimistic, but it's about like don't just say no. Like
Exactly.
if someone can do it, then let them do it. If they want to dedicate that, you can call them stupid, but you don't have to stop them. Like and just okay. Um, well, the answer is nuanced, and the critique of single layer perceptrons was technically correct, but they were pessimistic about the multi-layer networks in ways that turned out to be unwarranted. They didn't anticipate that computing power would increase exponentially, like we know from Moore's law. The number of transistors in a chip are going to increase by twofold every year. It has considerably slowed down now, but innovation in a different sphere is happening now. We develop massive data sets, which are the internet, so the context improves. We develop better initialization schemas and activation functions, and we discover that depth itself is powerful. So the lesson, which is beware of fundamental sounding arguments, but what's theoretically impossible. History is often written by those who didn't believe the critics. They also make fool of people and waste a lot of money sometimes. Um, Now we get into our fourth chapter, which is the final chapter of our paper here, which is the perceptron's enduring legacy, modern ML and robotics. The timing that we are looking at here is from 1958 to 2025, which is recent. And the thing that we want to outline here is, why does Rosenblatt still matter? We get to shift gears now. Rosenblatt did die in 1971 at the age of 43 in a boating accident. He didn't live to see the revival of neural networks, the triumph of back propagation, or deep learning revolution. But his core ideas, learning from data, adaptive systems, distributed representations, form the foundation of everything we do in machine learning today. Let me demonstrate this by tracing how perceptron concepts appear in modern ML and robotics. This is not academic archaeology. This is current practice that is actually happening right now. Logistic regression, the smooth perceptron. Let's start with the simplest connection, logistic regression. Logistic regression is taught in every machine learning course today. It's one of the most widely used models in practice. And here's what many people don't realize. Logistic regression is essentially a smoother version of the perceptron. Recall the perceptron's activation rule, sign summation of wi and activation minus the threshold.
Yeah.
This is a hard threshold. You're either above or you're either below. But in logistic regression, we replace the hard threshold with a smooth sigmoid function. Have you heard this word before? Sigmoid function. Sigmoid layer is the layer it's one of the layers that you use in training a machine learning model. Are we clear on the original function that we talked about? We are clear on that, right? Okay. Now think of that like theta that is there. We replace it by the sigmoid function, which is going to be something very simple. It's going to be sigma equals 1 over 1 plus or 1 minus?
1
1
plus.
plus e to the power minus z.
Yeah.
Okay. We'll replace it with this, where z essentially is the summation of the wiai minus theta. Okay. So z is representing that. So we are replacing this by, so we are replacing the theta by 1 over 1 plus e to the power minus whatever is written there. Okay.
Okay.
Yeah. We are
The formula is repeating itself.
yeah, so the formula is, yes, it is repeating itself and it's making it dynamic. Like that's what it's actually trying to do. The output of the logistic regression essentially turns out to be sigma transpose A. Okay. It turns out to be this. Like when you run it, it turns out to be this, where P cap is the predicted probability that the example belongs to the positive class. So what was this equation even being used for? It was being used to create a plane, hyperplane, and a line which would separate negative and separate positive, right?
Yeah.
When you replace the sigma wiai minus theta with this one over here, sigmoid 1 over 1 plus e minus z, then where z is essentially this, then you end up with p cap equals sigma w transpose A. You would originally get sine w transpose A, but now you get sigma w transpose A, which is essentially the probability, of classifying it as -1 or like negative or positive, where p cap is the predicted probability that the example belongs to a positive class. Okay. Why is this better than the perceptron? Because it's differentiable, because it's dynamic. It gives you a probability instead of a hard binary output. That's what he doesn't like. And critically, it opens the door to gradient-based optimization. You can define a loss function. You can define cross entropy loss. You can compute gradients with respect to the weights, simply because you have a probability now. It's not binary, it's not black and white anymore. It's on the spectrum. See, philosophy even comes in here, right? This is the foundation of modern optimization machine learning. This is the squiggly, right? But notice the core architecture is identical. A linear combination of weighted inputs passed through a monotonic activation function, producing a decision. This is the perceptron, but a little smoothed. The perceptron update as a primitive SGD. Here's another connection. The perceptron update rule is a special case of stochastic gradient descent. This is something that you will learn about like later in school. Recall the perceptron update. Weight new equals weight old plus learning factor times error times the initial activation, the function that I wrote over there.
Yeah.
Very important function. Now consider a loss function, say a misclassification loss, which is 1 if the sign of W transpose A disagrees with T, and 0 otherwise. Okay. If we compute the gradient of this loss with respect to the weights, we get something very close to T minus Y times initial A. In other words, the perceptron learning rule is doing gradient descent on a discrete loss function. Modern SGD is doing gradient descent on smooth differentiable loss functions. So the only thing is that was rigid, this is smooth. With carefully tuned learning rates, momentum, adaptive step sizes, Adam, RM Scoop, etc. talk about this. RS Prop, RMS Prop talk about this, etc. But the core idea, which is estimating the gradient on a mini batch, update weights in negative gradient direction, comes straight from Rosenblatt's perceptron. Every time you call dot backward in PyTorch, you're implementing a sophisticated version of Rosenblatt's learning algorithm. That's how relevant it is. Here's a question for you. What fundamental capabilities do modern optimizers like Adam or RMS Prop add that go beyond the perceptron's simple error correction rule? And why does it matter? Take the lead and answer here. Adaptive learning rates that adjust per parameter, momentum that accelerates convergence, second order information in some cases that improve update quality. These allow us to train deep networks that the perceptron could never train. Here's something that I want to make concrete for you. Every linear layer in a modern neural network is essentially a collection of perceptrons. I'll say that again. Every linear layer in a modern neural network is essentially a collection of perceptrons. Consider a standard fully connected layer in a deep network. Okay. If you look at the single row, you will have a vector which computes. This is exactly a perceptron. This layer that does a computation is a perceptron. It's computing a weighted sum of inputs, comparing to a threshold, which is the bias, and applying a non-linearity. It has weight, it adds a bias, and it is applying a non-linearity. The innovation of deep learning is that we chain many of these together, layer after layer after layer, perceptrons feeding into perceptrons with learned weights at every layer. This depth combined with non-linearities and massive data is what gives deep networks their power. But each individual processing unit traces its lineage directly back to Rosenblatt's perceptrons. Perceptron like, and now we get into some of the modern structures that are relevant. We'll go over three of these today, and that's the final takeaway. It's perceptron like structures in autonomous vehicles. Let's move into robotics and autonomous systems for a minute, which is closer to my research interests. In an autonomous vehicle or robot, perception pipeline involves extracting features from sensors, which are cameras, LiDAR, radar. You see Waymo, right?
Yeah.
Waymo has all of these and make decisions based on them. At various stages of this pipeline, you have classifiers that look remarkably like perceptrons, right? Deep learning network. Obstacle detection. Consider a perceptron module that takes LiDAR or radar data that needs to detect obstacles. The raw sensor data is processed through feature extraction layers. Then a classifier needs to make a binary decision. Is this point an obstacle or an empty space? At its core, this classifier is often a linear or semi-linear decision boundary, precisely what a perceptron computes. It might be a neural network layer, or it might be a learned SVM or logistic regression model. But geometric intuition is the same. Divide the feature space with a specific hyperplane and use that hyperplane to classify. Is this perceptron idea This is the perceptron idea applied to real sensor data. Very intuitive, right? Makes sense? Okay. Sensor fusion for localization, which is the second thing we are looking at. Many autonomous systems combine data from multiple sensors like IMU, GPS, LiDAR, visual, odometry to estimate the robot's pose and environment state. Sensor fusion models often use approaches like Kalman filtering or particle filtering. But at certain layers, Kalman filtering or particle filtering, but at certain layers, they involve learning weighted combinations of sensor observations, which is fundamentally what a perceptron does. You're learning which sensor should I trust? How should I weigh them together? What combination of signals indicates a particular state? These are perceptron like learning problems. Another example that we can look at is switching logic and control policies. Um, Yeah, another thing that we can look at is switching logic and control policies. In some robotic systems, the control policy involves discrete switching logic. For instance, if the robot detects an obstacle, activate obstacle avoidance. Otherwise, continue navigating toward the goal. This discrete switching can be modeled as a perceptron classifier. Given sensor observations and state information, output a discrete control action. More sophisticated controllers learn getting mechanisms, or example, a what if module that learns to switch between policies. These gating mechanisms often use perceptron like structures. Switching your policy based on the decision of the current perceptron. Like if it's a cow in front of my car, I'll probably brake. But if it's like a um
Speed bump.
speed bump, yeah,
Yeah.
you'll probably just like, I was
Mm.
gonna say child, but okay. Okay, anyways. Deep Q networks, DQN and reinforcement learning. Let me give you a more direct example from deep reinforcement learning, which is hugely relevant for robotics also. In a deep Q network, or DQN, which learns to play games or control agents, the architecture is a convolutional layers process visual input, fully connected layer process features, and output layer produces Q values for each action. Each of these layers includes a linear transformation followed by non-linearities.
Q network.
Hmm?
What is Q network?
It's a Q network has three parts: a convolutional layer, fully connected layer, an output layer which produces Q values. Q values can be thought of as this equation here. which will be QSA equals AI HI. Okay. HI plus what was that? BA. BA is gonna be your bias. But yeah,
What is that?
you can think of HI as a hidden feature
Okay.
and WAI as learned weights for an action A.
Yeah.
So HI, so this is also like W transpose TA
What is it
plus,
same?
it's literally the same thing, but like it's just that like, it's just that like, the hyperplane changes and like the dimension that you are looking at things at is changing. So to account for that, you need to have a more complicated like variable, and all that changes is this, but the fundamental remains the same. Here the HI are hidden features and WAI are learned weights for an action A. BA is, you tell me what BA is the bias. Yeah. This is evaluating a linear function of features, a perceptron, and that was very intuitive, right?
Yeah.
The Q-learning algorithm then uses this to compute a TD error and update the weights. The updated rule, while more sophisticated than Rosenblatt's, follows the same principle, adjust weights to reduce the error. So why modern systems are perceptrons all the way down? The deep insight. Neural networks, from the perceptron to modern transformers, are fundamentally about learning useful features for representations, learning useful feature representations, and using those features to make decisions via weighted combinations and thresholding. Both of these ideas come from Rosenblatt. Modern deep learning has added layers, nonlinearities, better optimizers, more data, and massive compute, but the core operation, which is weighted sum of inputs passed through an activation function, is the same. The perceptron is not obsolete, it's foundational. The continuity of ideas. Here's a question that ties into my work, a little bit of my work, which is in our robotics or ML projects, can we identify places where we are using perceptron-like architectures? How would we think about continuity between Rosenblatt's 1958 machines and our modern systems? Does anyone want to answer, or do you want me to just quickly answer this question? No, they are ROTC.
Oh, okay.
Yeah. Does anyone want to think about this, or should I give an answer here?
Can you repeat the question?
Yeah, the question is like in a robotics or ML project,
Yeah.
can you identify places where you're using perceptron-like structures? How do you think the continuity between Rosenblatt's 58 machine and our modern systems are alike? We just went over 3 examples. Can you think of something else?
I know you mentioned like memos and stuff, right?
Yeah. How about like a Roomba?
Really?
Yeah. How about like a Roomba that has computer vision and maps your room?
Okay.
It does
It
take
makes a
sensor
picture.
information and makes a room map, but what exactly is that room map? It's a higher dimension version of a perceptron.
Okay.
And it actually like has a weight and bias towards if I move 15 steps forward, then I actually encounter a wall. But maybe that was not a wall. Maybe that
Runs into a dog.
maybe that was a dog.
Yeah.
So, next time it goes there and it doesn't see anything, it updates its values and it knows that now I can actually go there. What if it was not a wall or a dog, but it was a sofa? And 6 months later, the owner decides to move that sofa. Now, when it's moving again, it updates its layers
That's
again.
after every start of the room.
No, that would be very highly inefficient, right?
Okay.
Like it can have like whenever it sees something that was unconventional to its original idea, that's when it starts mapping it,
Yeah,
right?
yeah.
So that's an idea where I can think of robotics coming together. Mo, do you have something from bio-inspired machine learning where you can think about Rosenblatt's perceptrons?
Not really, because a single perceptron network would be difficult for predicting anything, because bio would involve predicting, reading a lot to predict something, and the single perceptron just didn't have enough context to be applicable.
Yeah. Okay. Let's see what we have learned since the perceptron. This is like, I promise, like we are coming to the conclusion now. Okay. Let's see what we have essentially learned, from the perceptrons that we have been talking about for quite some time now. Okay. Depth is essential. A single layer perceptron cannot solve nonlinear problems, like our friend just said. But we now know that depth stacking many layers is crucial for learning complex functions. This is why deep learning works. Representation matters more than raw compute. This is the second outtake. Representation matters more than raw compute. The random projections in Rosenblatt's A layer were a workaround. Modern systems learn the representations end to end, which is more powerful. But the insight that finding a good representation is often the hard part. It remains true. Nonlinear activations are essential. Rosenblatt's perceptron used hard thresholds. We now use smooth, nonlinear activations, sigmoid, tan, ReLU. These are all the functions that you'll probably use when you're learning PyTorch. These enable gradient-based learning and allow networks to model complex functions. Fourth, data scale matters enormously. Rosenblatt didn't have much data, but modern deep learning consumes billions of examples. This data, combined with computational power, is what has unlocked the potential that Rosenblatt dimly saw. Fifth, the curse of dimensionality is real but manageable. High dimensional spaces are counterintuitive, the curse of dimensionality. And this was a concern for Rosenblatt. Modern deep learning, combined with regularization and architectural innovations, has learned to navigate high dimensional spaces very effectively. Some encryption problems are in 500 dimensions. Can't even visualize that, right? Like you can't even visualize that. Like think of it like every new layer, that is added. Like,
Yeah, exactly.
and this is still like, can't like even think what it is. Okay, there are genuine there are genuine debates about this. Some researchers think neural networks might give away to hybrid approaches combining neural and symbolic systems, like I was saying before. And others think that we'll move toward different architectures like attention mechanisms, which are starting to replace traditional perceptrons in some contexts. But I suspect that the core idea, which is attention architecture, well, I haven't heard of it yet until I started researching for this paper. But let me get back to you after this session about that. I think I'll get back to you about that after this session. I do suspect that the core idea, though, that local adaptive learning rules that adjust weighted combinations will still persist. Um, like I said before, I'm a believer of the neural, but there's also this idea that it might actually be like a combination. It's deeply aligned with how both brains and computers work. Now for the conclusion, reflection, and synthesis. The perceptron in hindsight and the future of AI. We have now spent 75 minutes with Frank Rosenblatt and his perceptron. And let me try to synthesize what we have covered and reflect on why this 1958 paper still matters to you, the listener, in 1925, in 2025, as a computer scientist working on AI and robotics. The perceptron as a historical turn point was indeed a historical turning point. Before Rosenblatt, AI was largely symbolic, logic, and rule based. And after Rosenblatt, there was a compelling alternative, which was learning from data, adjusting weights, and letting patterns emerge. The Minsky-Papert critique showed that Rosenblatt's vision has limits, but those limits were on a single layer network, not on the learning itself. Once researchers figured out how to train deep networks, which took decades, Rosenblatt's core ideas were vindicated. Uh, this humbling lesson, transformative ideas often face fierce resistance and setbacks before they are recognized as transformative. Rosenblatt didn't live to see his vindication, but his ideas did. The perceptron as a technical foundation. More concretely, the perceptron established a concrete model of how learning could work in networks of simple units, a mathematical framework, the convergence theorem for analyzing learning algorithms, a learning rule, error correction that generalizes to gradient descent, and the insight that general models in sufficiently rich feature spaces can be powerful. Every one of these ideas is foundational to modern machine learning and deep learning. The perceptron also posed a philosophical statement, which was perhaps most importantly a philosophical statement that goes like intelligence is adaptation, learning is central. Simple local rules applied across many interconnected units can produce intelligent behavior. That's what thought is. You learn about so many different papers, you put these ideas together, and you end up with new ideas. That's why you'd go to ACM ARC, bro. Another plug. This contrasts sharply with the symbolic AI view. Intelligence is symbol manipulation, knowledge is representation, reasoning is inference from explicit rules. This is rote memorization. That's what it is. That's why I don't believe in it, but it does work. We now know that the truth is probably somewhere between these two extremes. Intelligence likely involves both from learning and reasoning. both distributed representations and some forms of symbolic structure. But the balance has shifted heavily towards Rosenblatt's vision now. As we move towards graduate, research work, and we think about some programs that are offered at ASU, like robotics and autonomous systems, the Perceptron's lessons are directly applicable. Representation learning matters. Learning is more powerful than handcrafted rules. Depth is essential. Mathematical rigor matters, and history is our ally. I would like to clarify on that by saying that understanding where your tools came from, not just their names, but their foundational ideas, make you a better researcher. It helps you see new possibilities and avoid old mistakes. You can practice all you want, but you do need to know what you're dealing with. Okay. We now end with a final reflection. Before we close, I do want to ask you one more question, and I want you to sit with it. What do you think is the most surprising thing about Rosenblatt's perceptron? What did you expect out of it before you came for towards arc session? Like, what was the thing that would come to your mind, and what did you actually learn? Think about that and reflect on some of these concepts that we talked about. there's a there's a heavy lesson in the concepts that we learned today, and it does have to do with the foundations of learning itself. A lot of this might not be directly applied, like the Pythagorean formula,
Yeah.
but hidden nuances, it affects your life on a day-to-day basis, and you make decisions that you don't even know because because it's based on the perceptron. Even your own brain is uh
You don't know that.
complicated
Yeah.
um version of a perceptron to some extent. It is a neural network, I'll tell you that.
Yeah.
As you continue to work in AI, if you do, remember that you are standing on the shoulders of giants like Rosenblatt.
Mhm.
The architectures that you use, the algorithms that you implement, and the problems that you're trying to solve, all of these trace their lineage back to 1958, and more broadly, they trace back to much more old ideas about learning, adaptation, and the nature of intelligence. Perceptron is not just a historical artifact, it's the foundational idea that continues to shape how we think about and build intelligent machines. And with that, I would like to end today's ARC session. Thank you for all who could make it. There's the original paper, the Rosenblatt Perceptron, Probabilistic Model for Information Storage and Organization in the Brain. But there's also the foundational critique by Papert and Minsky, Perceptrons: An Introduction to Computational Geometry by the MIT Press. There's also some historical concept by Wiener and McCulloch and Pitts, the cybernetics that I was talking about, and logical calculus of ideas immanent in nervous activity. And there's some work on backprop and model learning by Ian Goodfellow and Rumelhart, Hinton and Williams. And there's modern applications by Hinton, Bengio, and Lacoon. This paper was published in 2015, and this was the effective boom. 2015, deep learning
Yeah.
in the Nature magazine. And everything that happened after that is just history unfolding itself in real time right now. But with that, I would like to end today's ARC session and extending a heartfelt thank you for everyone who could make it. All of these resources will be provided in the video description too for anyone interested in reading further. And yeah, we move forward and we keep learning. And see you guys next week for the next AI paper.
That's it.